times, but yeah. Okay, so thank you very much for keeping your energies till now. I will try to give a very short and smooth talk so that we can end with these talks fast and then keep on discussing. So I may just yeah. So I'm going to give you recent results on a method that I've been working on recently, a hybrid method coming to these NISQ devices, a hybrid method to approach frustrated quantum models on 2 dimensions and to specifically describe valence-bond solid phases. This work, you can find it in arXiv and has been funded by this project, so the European Commission through Open SuperQ and CFRF here in Quantum Matter Institute. So the main idea is that we have a Hamiltonian that it is physically motivated, and we would like to know which is the ground state, but more specifically, which are the correlators, defining the features of the phases emerging in the system. Let us take for simplicity a square lattice where we have spin 1/2 degrees of freedom on each vertex. And one approximation to this Hamiltonian in 2 dimensions, one very easy approximation actually, is just a cluster-Gutzwiller ansatz. This is just a simple uncorrelated product of n spin wave functions that are patching the whole or tiling the whole 2-dimensional infinite lattice. Like here, I'm sketching just 2x2 clusters in blue. And this, when we variationally optimize the parameters theta by taking the expectation value of the Hamiltonian, this is equivalent to solve the same Hamiltonian in a finite cluster with open boundary conditions, and now with a mean field embedding that is pushing in all the information about the thermodynamic impact. Now, this method has an exact limit, which is obviously when our cluster is increasing with increasing size, so in the n infinite limit. But obviously, we cannot get this exact limit. We are limited by classical resources to around 30 spins or 30 qubits due to memory. So the idea in this method is to replace this classical solver, this exact diagonalization or Lanczos, by a parameterized quantum circuit, and the parameters defining these gates are tuned so as to optimize the expectation value of the Hamiltonian now in the thermodynamic limit. And this because the ansatz is variational, so by the variational principle, this gives us an upper bound to the exact ground state energy. I will give you some benchmark results on the J1, J2 Heisenberg antiferromagnet, where we can actually describe the Nel antiferromagnet, and then by changing this ratio of J2 over J1, we can describe a valence-bond solid phase, which is a quantum paramagnet with this placket structure, so 2x2 strongly correlated or entangled plaquettes. So the outline is as follows. So first, I will give you some words about variational quantum algorithms, a general framework, potentialities and known limitations from recent works, few words about frustrated magnets in 2 dimensions. Then I will pass and give you a couple of details on this cluster-Gutzwiller ansatz, and some details on the heuristics on the construction of this quantum circuit ansatz. And then I will pass to these numerical results, state vector numerical results to the J1, J2 Heisenberg antiferromagnet, and then I will give you the summary, if I have time, the outlook. So variational quantum algorithms, they share this general structure where we have a quantum device, these so-called noisy devices, providing a quantum state through this parameterized quantum circuit that hopefully encodes correlations among data efficiently. And we are measuring it, and these measurements allow us to construct a cost function that is optimized so as to find the extrema encoding the solution of a given target problem. So, for example, the variational quantum eigensolver that you may have heard about a lot was proposed to quantum simulate finite strongly correlated systems in quantum chemistry, or the quantum approximation optimization algorithm, which has been proposed to approach combinatorial optimization problems. So in the first case, we have that the cost function is the energy simply of this Hamiltonian, and in the second case is some kind of an energy of an Ising Hamiltonian in some irregular lattice, like this max-up and max-cut problems. So although the initial expected potentialities of this like very natural framework of combining small quantum devices with the power of current CPUs, recent work has shown that indeed this optimization landscape is impeded by numerous roadblocks, and specifically these barren-plateaux, which are like large flat regions in the optimization landscape. And they are originated at this phenomenon of concentration of measure, which makes the observables to concentrate around their average in the Hilbert space. And this makes, therefore, that the derivatives, so the gradients of these cost functions are essentially zero, and most importantly, that the variance vanishes exponentially with the system size. But not only that, this phenomenon of barren-plateaux is cost function dependent. It has been proven that global cost functions under certain circumstances for randomly initialized circuits, they show barren-plateaux, while local cost functions like the expectation value of local Hamiltonians may be trainable. They depend also on the depth of the circuits. Deep or expressive circuits are mostly prone to this effect, while shallow or inexpressive circuits are not or may be trainable. And this is independent of the optimization routine, whether it is gradient or gradient free, it doesn't matter. But on top of that, on top of these flat regions, we have also that they show multiple suboptimal extrema. So I will try to pass by this window of possibility, and I will try to explore circuit heuristically constructed by the information that we know from the Hamiltonian by symmetry. We will try to construct a circuit that may avoid this barren-plateau phenomenon. So a couple of words on frustrated quantum magnets. These are, in general, local Hamiltonians, where the local energy constraints imposed by the Hamiltonians cannot be efficiently satisfied under the name frustrated. And this is linked to the notion of non-stochasticity that was also explained by David Gossett the other day, that oh, here there is it should be strictly positive. So when you have off-diagonal terms in the Hamiltonian that are strictly positive, and this is rooting the sign problem in quantum Monte Carlo, which is the state-of-the-art classical algorithm to approach large spin systems in 2 dimensions, and therefore we do not have this tool. So this sign problem, which makes it NP hard, even finding a proper basis, so of V and W, to mitigate this sign problem, because this is a basis dependent problem, even it has been recently shown that it is an NP hard problem. So frustrated quantum magnets are an ideal arena to test these algorithms, as they pose, as you see, numerous challenges to classical algorithms. Plus, they lead to, they host competing quantum paramagnets that I may classify very briefly here by those which break translational invariance, valence-bond solids, or those that preserve translational invariant that we may call very vaguely as quantum spin liquids, and you can put in that box all short-range entangled or long-range entangled phases or critical, etc.
I'm sorry, Daniel, I didn't quite understand. So not stochasticity. What should be the equation? It should be V.
Strictly positive, not zero. If it is zero, it's strictly positive, not the equal.
I mean, so somehow it's a complex number. So like phases, like so the problematic thing is only if they're exactly positive. Like the problematic thing is anything except only positive.
If you have complex, I think you have also sign problem. Yes, I would say so, because you can always put it as
yeah, so if this matrix element is, so when do I not have a problem?
When you have when they are negative.
And they're strictly negative.
Yes,
that's the only case where.
Yes, but okay. If your Hamiltonian is Hermitian, your these matrix elements are real. Not always. No. Yeah. When you do not have a problem is when it is negative. Yeah.
Thanks.
So one example is this J1, J2 Heisenberg antiferromagnet. I have sketched just the nearest neighbor Heisenberg interactions by the black lines and the next to nearest neighbors in red lines. This was originally motivated by the physics of high temperature. Still under debate, which is the quantum paramagnet phase that lies between this long-range order Nel and the long-range order columnar antiferromagnet. So there is, since the 90s, a bunch of work and has been the battleground of all numerical methods. So this can lead either to a valence-bond solid phase, breaking C4 lattice symmetry of the lattice, or a plaqued valence-bond solid preserving C4 symmetry of the lattice, or quantum spin liquid. So here I'm using this gray region to somehow sketch entanglement in your phase. And recent DMRG results of Gong and co-workers have argued that there is this transition to a valence-bond solid through a quantum spin liquid phase.
Whenever you say quantum spin liquid here, is what you have in mind like when it's resonating valence-bond solids, like sort of
So resonant valence bond solid, you would put it in the quantum spin liquid.
Okay.
Yes.
But I guess it can be more general than that.
Yeah, I do not remember precisely this work, whether it was gapless. So resonant valence bond solids, in general, as far as I know, they are linked to topological, so intrinsically topological order phases, Z2 phases. Z2. I do not remember right now whether the work of they were, I think they were claiming for a critical. So you want this U1 criticality, U1 quantum spin.
I see.
So this has been also like the original works of Redas and Ansatz, and there is also a lot of other work claiming that there is Nel to valence bond solid with dimer order, and that is a continuous phase transition that lies out of the Landau paradigm. So there is some critical point, but there is no group-subgroup relation between these two valence bond solids. So that was also another picture of it. Moreover, it has been shown also in numerical grounds with exact diagonalization that when adding a next to next nearest neighbor to this Hamiltonian, so a J3 term, that stabilizes this valence bond solid phase. And recent DMRG results by Daniel González Cuadra have argued that this plaquette valence bond solid phase is indeed a higher order form or of SPT by computing entanglement spectrum. DMRG, I think 9 by 9. So in any case, the idea to retain is that in the thermodynamic limit, we may have a handful of orders, and in this case, in SU2 Hamiltonians, we may have U1 preserving orders, and therefore we can take this information to construct some inexpressive, some shallow parameterized quantum circuit that may avoid these barren-plateaux. So just to give, before giving you the details on the parameterized quantum circuit construction, just a few words on details on how would it be this cluster-Gutzwiller for the J1, J2 model. So for the case of 2x2 spins, what we have just to do is to measure this local spin and two spin correlations in the cluster, and then we can construct just out of that an energy in the thermodynamic limit. So we have some internal part of the cluster, and then we have also here this second term, which is the mean field coming from the interactions between in the beginning two clusters. So the cluster and the mean field embedded, and we can assess the phase diagram that we got with 2x2 by scaling and taking 4x4 cubic clusters. So how do we construct this quantum circuit ansatz? There are many constructions. Typically, they are breaking U1 symmetry. Also, others are based in protorizations of the Hamiltonian that one wants to simulate. Here, I will just take this U1 symmetry of these states and realize that indeed the 2-qubit U1 subspace is generated by this SU2 algebra effectively. So we can find these S tilde operators that are indeed the XY Heisenberg interaction, the XY or the Z projection of the Dialog-Szyński-Morilla interaction, and the staggered magnetization. And we can put this in a block sphere very nicely and see that if we take a simple 1-0 state and entangle by a pi-half rotation, we can, around the S tilde Y axis, by a pi-half rotation, we can efficiently generate this singlet or valence bond, which might be one of the building blocks of this valence bond solid phase. So this real XY gate can be understood as a generalized Givens rotation. So Givens rotations are rotations in a larger space, generalized because now we are in a hyperspace, in a complex space, and has been used or proposed for the quantum simulation of fermionic Slater determinants. And moreover, recent results, experimental results by Righetti, have shown that like general rotations in this sphere can be get with fidelities of 97. So for 2x2, we try to construct the quantum circuit ansatz just by trying to preserve as much as possible the C4 symmetry of the original lattice, so that we also have some shallow circuit ansatz and stay always in the U1 subspace. So we apply these real XY gates, and then to add phases to the wave function, we add some Z0 rotations and local Z rotations. So this has a macro layer, if you want, of 5 layers, and we repeat this structure several times, m times, so as to improve the accuracy. For 4x4 qubits, I repeat the same structure, preserving again as much as we can the C4 symmetry of the lattice, and we find this 9-layer structure that we can repeat again several m times till a total depth of 9m. And interestingly, by this structure, we can indeed, with this same depth of 9 layers, we can go up to 6x6 qubits. So we have a structure which has a finite depth for n even number of qubits. So some state vector results, as if we had like a very, very efficient machine, and in order to see whether this quantum circuit, although it is inexpressive, it can give us a good approximation to the classical results that we can obtain in our computer with the original classical cluster-Gutzwiller approximation. So here is the ground state energy. I am plotting with black the classical cluster-Gutzwiller results. So that is 2x2 with the stars and 4x4 with black dots. And then with this quantum circuit, so the hybrid, idealized hybrid method, I am plotting them with the gray 2x2 and 4x4 with M2 macro layers in yellow and 4x4 4 macro layers in red triangles. So first of all, we can see that with just 2 macro layers, in the 2x2 case, we can exactly reproduce the numerical results of the classical cluster-Gutzwiller approach. We can reproduce also, therefore, the derivative of the energy, which shows a continuous first derivative around 0.4. If we were to do the second derivative, we would see a jump, and then a jump signaling a first order transition around 0.6. And then when we increase the cluster size, we can see that although we do not get exact the same results as the classical cluster-Gutzwiller, we can see that in the regions near to 0 and near to 1, that we will see that they correspond to the ordered phases. We have very good quantitative results that even improve when increasing the macrolayer number M to M4. And in the phase in between, that we will see that it corresponds to the valence bond solid phase, where we have the worst approximation to the classical energy. We have also some increasing of accuracy when increasing the number of macrolayers. So one nice thing about this cluster-Gutzwiller wave function is that we can compute order parameters, because these mean fields break explicitly the symmetries of our Hamiltonian. So contrary to exact diagonalization, that we have to infer the order parameters by scaling the peaks in the structure factors, we can just here compute these observables directly. So we can see in open points the pi wave vector of the magnetization, which corresponds to the Nel order parameter, and with field points the 0 pi wave vector of the magnetization, which corresponds to the collinear antiferromagnet. And we can see a jump around 0.6 that corresponds to our first order phase transition, and then we can see that there is a continuous from the gray points that correspond to the 2x2 cluster, or the black points that corresponds to the 4x4, the classical results. They are continuous, the same as in accordance to the derivative of the energy. And we can see that the hybrid algorithm, as we increase the number of macro layers from 2 to 4, so from yellow to red, this jump that we see, that in principle would, that it corresponds to a first order phase transition, it is reducing towards the classical results. So it is reducing toward a weakly first order that we conjecture it may tend to the second order as we increase even more the number of macro layers. So to characterize this phase here that has this quantum paramagnetic phase with no magnetization, we compute this dimer observable, which, as you see, it is not an order parameter, because the translational invariance or the translational symmetry is here. It is not a continuous symmetry. So we have finite values also in the order phases, but if one would do a scaling analysis, one would see that they tend to 0 in the thermodynamic limit. But the important part is here between 0.4 and 0.6, where we see with 2x2, which is in gray, that we have a plateau, and with 4x4, which is in black, those are the classical results, show a quasi-plateau. And interestingly, okay, with 2x2, again, we are reproducing the classical results. But with 4x4, we see that upon increasing the number of macro layers, so from yellow to red, although the C4 is broken by this hybrid method, as we are increasing the number of macro layers, again, the results show that C4 is starting to be recovered. So again, another sign that increasing the number of macro layers, we may find more and more accurate results towards the classical cluster-Gutzwiller.
Question?
Yes.
How do you see from the data that the C4 symmetry is recovered if you increase the number of layers?
Well, this is the conjecture that I'm saying, that so yellow points correspond to M2 macro layers, while red correspond to M4. So here the jump is bigger for M2, and here it is reducing. Well, here it is even very small, and here it is much less the jump between the red than the yellow. So the difference between the dx and dy is reduced. Now, it is possible that it is a conjecture. So it is possible that maybe one only recovers C4 in the n infinity limit, because we are using 2 qubit gates. So it is natural that this ansatz is indeed breaking C4 symmetry, although we are playing this game of trying to recover it.
Yes, but you're getting closer if you have more.
It gets closer, yes.
Smaller rotation.
But to be precise, the valence-bond solid that is representing these red lines is a placket valence-bond solid, but has a strength greater along one of the directions than in the other. So it is not C4 symmetry. So and the last benchmark result is the convergence, to see how this hybrid algorithm would converge, whether how the barren-plateaux may affect. So here I'm showing results for 4x4 cluster with M2 macro layers, 10 random initializations of the parameterized quantum circuit in orange, and the reference results are the black dots that correspond to the 4x4 classical cluster-Gutzwiller. We can see that the energy, most for, I think, eight of the initialization, random initializations, they are tending towards the classical result, except 2 that are indeed tending towards a single suboptimal minimum. And we can see upon computing the magnetization with wave vector 0 pi, that is signaling the columnar antiferromagnet, that indeed they are pushing the convergence, the onset of this magnetization, which is carried out by the mean fields, is pushing the convergence of the algorithm, and that actually the suboptimal minimum, they correspond to suboptimal magnetization. I would like to stress that this convergence is for J2 equal to 1. So if we were to think about parameterized versions to simulate this Hamiltonian, we would need 2 qubit gates that are linking qubits in opposite directions of in the square lattice, in the plackets of the square lattice. So just to summarize, I have introduced this hybrid method to simulate 2D magnets in the thermodynamic limit, and it relies in 2 main pillars. One is the parameterized quantum circuit that I have given you some heuristics how to construct it, which is U1 symmetric, and I am using this real XY gate that I have defined by unveiling this SU2 symmetry of the U1 symmetric 2 qubit subspace. And as I have stressed in this last convergence, it respects the square connectivity that current experimental groups from Google or ETH they are using, and it relies also in the definition of the cost function, so the energy that has implied this thermodynamic limit through the mean fields. And these mean fields are the ones that are pushing the convergence in the long-range ordered phases. And we can describe the valence-bond solid phase by tuning smoothly the Hamiltonian, the target Hamiltonian, and then crossing a quantum phase transition that we were seeing that it was first order, but as we increase the number of macro layers, we could see that it was tending towards weakly first order, we hope second order. So just to give a few items of outlook, it would be nice to have 6x6 benchmark simulations, but this requires an efficient simulation strategy like parallelization or the tensor network representations described previously in the workshop, it would be nice also to explore different native XY gates, and in particular the trapped ion collective XY gates that may preserve this C4 symmetry inherently because they are long-range gates. And then one cool thing about this is that we can use an exactly solvable model with valence-bond solid as an exact ground state. So a parent Hamiltonian of a valence-bond state as a means, so the simulation as a means of benchmarking either the algorithm or also the NISQ device. And yeah, I would like to just leave here for maybe discussion, continue with this morning discussion about SPT 2 dimensions, whether this valence-bond solid higher order SPT would have any implications for quantum computation. And with this, I would like to finish, and I'm looking forward to your questions.
So what was the take on the university of Paris method? And it is going to work for something with very, very long range of direction to liquid kind of solution.
Yes, those would lie. So how to characterize the spin liquids is a question that with this cluster wave function, it's a question that we are currently working. Obviously, the cluster wave function is breaking transitional environment. So just by a matter of how simple this or uncorrelated your cluster wave function is, you know you cannot describe the translational invariant state. But we are working on which are the artificial signatures. How can we infer from these artificial signatures of artificial means? How can we infer whether we are having indeed some translational invariant state? And specifically, we are working on benchmarking this on the Kira model. So in principle, the quick response would be no. You cannot describe quantum field. But the refined response to this no would be, okay, we may have, so indeed we may have, by elaboration on the artificial signatures, we may have a way to infer that there might be some quantum field. So in principle, no. And the phase transitions that we can see in the classical ansatz are Landau type. But then, then the question is to refine how can you infer something which lies up of this frame.
And the complexity of this method is like scaling really how the number of things in the cluster, right?
Oh, you mean the classical wave function or the hybrid? So the classical wave function has the same problem of ED, of hexagonalization. You cannot fit.
Yeah.
And that's why I am trying to provide some quantum circuit heuristics, some shallow things with fixed depth to try to overcome this limitation.
Yeah. So this quantum hybrid thing is currently so you need to apply some gates, and if you do it with current mixture of things, so do you think it's highly complicated to get this?
I think it is not very complicated. So so this is still the y. Indeed, just by putting some pi half rotations in just one of the qubits, you can use just the simple XY Heisenberg that are native to Google, for example. And they have some control Z that they have this fermionic sim gate. So one can play around and find a finite depth circuit. Of course, this finite depth circuit is not giving you what would be the classical Gutzwiller result, but an approximation to it. But what I was trying to provide or explore here is whether this approximation would fit with what we have classically at the sizes that we can compute classically. And so far, seems good. How, if we go to 6 by 6 and so on, putting aside problems of coherence and so on, that's another step. But it seems feasible. Yes.
So I have a question about barren-plateaux. So there's this technique called dropout. There's this technique in the classical machine. So classical machine learning also has some mild version of barren-plateaux. And one way to combat it is called the dropout. So basically, you have some, say, a network, or like an neural network, for example, and you take some random set of neurons, small one. So you train it, then you take some random set of neurons and just delete them, throw them off, and train it again and like keep repeating it. So what it ensures is that the kind of battles it getting stuck in some places, and it also ensures some robustness of the approach. If certain things don't go well in one region, they still go. So, can you repeat how the method again? So you have some ansatz with some operations for quantum devices that would be gates, and then you throw out some gates for computers, and you train your ansatz. So part of you fix some of the parameters and you train part of them, then you train another part. Yeah, you do not even like fix them. That one way is to fix them, the other way is to indeed like throw all the whole game constituted by identity. Yes. I kind of wondered if there is work. Forgot the first author, 2020. Yes, there is a similar thing in this quantum surface. Yes. So I heard about Maria Schultz doing that. So I kind of like wonder if it will help this kind of photos. It seems from numerical experiments that they have done, it seems to be the case. So we initializing instead of in a random with a random set of parameters or with a random circuit. So initializing with everything to identity. Yeah. Also, like if you look at the barren-plateaux papers, a lot of them kind of like hinge on the continuity, so that like gradients vanish, or the gradients vanish, and things like that. But if you like throw a whole gate out at some point, it's not a smooth operation. So kind of wonder if it would help with this getting unstuck from the community. Good export. Yeah, nevertheless, what is impressive is this, that the mean field which is pushing convergence, and I would show the
absolute value of the gradient, we can see that it increases when it changes the order parameter. But of course, I'm not sure yet whether here the problem of barren-plateaux is pushed away towards something that it is almost converged, but one can still converge even or by other methods, by trying to play with how you are optimizing, you may even get closer to the exact, exact, to the classical cluster Gutzwiller.
All right, so the speaker is around. We can ask questions later, so let's thank them. Yeah.